Hi, everyone. Thank you so much for watching our talk, Specifying and Testing GPU Workgroup Progress Models. My name is Tyler Sorensen. I'm an assistant professor at UC Santa Cruz. My collaborators are Lucas F. Salvador and Harmit Raval. These were two undergrads at Princeton University who I had the pleasure of working with while I was a postdoc there, and we worked with Professor Margaret Martinosi. We also collaborated with Ali Donaldson and John Wickerson at Imperial College London, and Hugh Everard, who is now at Google. So this is a big project with lots of people from different places, so it was a lot of fun. Now I know normally I would give the talk and you would ask the questions at the end, but this time I'm going to start off by asking you a question. That question is, how do you implement a mutex? Now, if you've done any sort of concurrent or parallel programming, this should be a pretty straightforward question. And why is that? It's because mutexes are foundational idioms in concurrent programming, so much so that in the classic textbook, The Art of Multiprocessor Programming, Chapter 2 is devoted to mutual exclusion and mutex implementations. So this is chapter 2, right after the introduction. And you would find many different implementations in this book with many different properties. Now I want to refine the question a little bit and ask, how do you implement a mutex on a GPU? This is a reasonable question because GPUs are parallel devices, so we might want mutual exclusion on them. And GPUs are pervasive. They're in the data center in the cloud that we interact with. They're in our performance workstations, our laptops, our phones, and sometimes even our watches. And since mutexes are one of the first things we learn about in parallel programming, we might want to know if we can implement them on these pervasive devices. If we're going to implement a mutex on a GPU, we're going to have to argue that it is correct. And when I think about correctness, I think to Tony Hoare. So Tony Hoare defined total correctness as having two components, safety and liveness. A safety property says that something bad will never happen. For mutex, this probably considers memory consistency, mutual exclusion, and reasoning about interleaving executions. And there's lots of great prior work on reasoning about safety properties for idioms like mutexes on GPUs. But this work, we're going to look at liveness properties. And a liveness property states that something good will eventually happen. And there hasn't been much work on this related to GPUs. And so we're going to explore for a mutex what sort of liveness issues might occur. To do this, let's look at a simple mutex implementation and a small test case using that mutex. Here on the left-hand side of the slide, we have two threads, thread 0 and thread 1. Both of these threads acquire a mutex and then immediately release the mutex. Now, the mutex implementation we've used here is a spin lock using an atomic exchange. How this works is to acquire the mutex, you spin on the atomic exchange on a shared variable m, and you exchange the value 1 to this shared variable m. And you spin while you see 1 in this location, meaning that the mutex is being held by another thread. Now, when you see 0 in this location, you're able to acquire this mutex and enter the critical section. To release the mutex, you simply store the value 0 to m. So in this simple test case, we can see thread 0 spinning to try to acquire the mutex and then immediately releasing it with this store. Similarly, thread 1 is spinning, trying to acquire this mutex and then immediately releases it with the store. So now, while we could stare really hard at the source code and reason about it, how we like to reason about concurrent programs is with a graphical model called a labeled transition system, and or an LTS. And we're showing the LTS for this small test case on the right-hand side of this slide. How this works is the circles are the states and the arrows between the circles are transitions or actions that threads can take that move us between states. So for example, at our start state A, two things can happen. Thread 0 can acquire the mutex or thread 1 can acquire the mutex. Let's say that thread 0 acquires the mutex. So that puts us into state B. Now what can happen here? Well, thread 1 can spin trying to acquire the mutex, but it wouldn't be able to acquire the mutex because thread 0 has the mutex. So it would spin and spin and spin. Eventually, T0 would release the mutex, putting us in state C. That would allow T1 to acquire the mutex, putting us in state D. Then T1 would eventually be able to release the mutex, and this test would terminate at state H. So what can potentially go wrong with respect to liveness issues in this test case? Well, what can happen is you start at state A, and let's say T0 acquires the mutex. What can happen is that T1 can sit here and spin indefinitely on state B if the system starves T0. That is, if the system never gives T0 a chance to release the mutex. And in that case, the simple test case would spin and not terminate, which is not correct behavior for a mutex. Because we're computer scientists, we like to generalize and abstract. And that cycle that we saw in the mutex example, well, we can generalize that to several patterns that can cause liveness issues in concurrent programs. The first one is called the starvation cycle. And this happens when the program hangs due to the system not executing a thread. And this occurs, for example, when you're in a state and one thread, say thread 0 is spinning, and thread 1 could free thread 0, but the system never gives thread 1 a chance to execute. You say thread 1 was starved, and that leads to a starvation cycle here. The other example is called the live lock. This happens when the program hangs when 2 or more threads are constantly interrupting each other. Here you can see thread 1 and thread 0 going back and forth, whereas if thread 1 was to execute twice, it would break out of this cycle. You could imagine this as being in a hallway and playing the back and forth game with someone, and imagine that happening indefinitely. Now, classically, starvation cycles are resolved with what's known as weak fairness, and live locks are resolved with what are known as strong fairness. And we won't get too much into the details of what actually differentiates those, but we do have sort of a foundation on where to start our reasoning. Now, what we'd like to do is be able to reason at a very precise and fine-grained level about what sort of cycles are guaranteed to eventually terminate. And a formal model that lets us do this, well, we call that a progress model. And if we have a progress model, then we can reason about all sorts of fine-grained synchronization, not just mutexes, but synchronization barriers and concurrent data structures. And once you're able to reason about those programs, it unlocks a whole host of applications such as work stealing. And these applications can have big performance benefits. So it seems like we'd want progress models for all of our concurrent processors. So why are we focused on GPUs in this work? Well, we see that GPUs are a really pragmatic target for this sort of exploration because current GPUs do exhibit non-termination behaviors due to starvation and live lock for some idioms, but not others. So it so happens that you can program a mutex on modern GPUs and it tends to work, but a synchronization barrier will lock up. That's pretty curious. Now, GPU programmers have created what we call folklore progress models. They've kind of experimented and found out what works and what doesn't work. And they end up writing programs based on these assumptions. And some of their applications actually get really good performance. Now, if you were to go to the specifications and actually try to reason about these programs, you would find that the specifications are often lacking. Either they don't give any progress properties or they aren't very clear. So this is sort of a combination of tensions here where GPUs are somewhat fair, but not completely fair. Programmers seem to have gone off spec to write what works, and specifications don't really address this. So that's why we think GPUs are a good target for this sort of exploration. And that brings us to this work. This work is a toolbox for specification designers when thinking about progress models. This toolbox contains executable semantics so that designers can write small programs and run them through a model checker and get answers to questions about liveness properties. We have test case synthesis. So we have a synthesis engine that's able to produce progress litmus tests. We are able to produce 483 progress litmus tests, including tests corresponding to common synchronization idioms. And using those tests, we were able to collect a large amount of testing data. We ran all of our tests on 8 different GPUs spanning 4 different vendors and 3 frameworks. One of our key results is that we refuted a hypothesis in prior work that suggested that they had a progress model that described modern GPUs. We actually showed that there are some tests that can deadlock on modern GPUs that they thought would pass. So we think that that's a pretty interesting result. Now, before we get started, I just want to iterate our focus here. We are interested in inter-workgroup thread interactions on GPUs. GPUs have a hierarchical programming model. Threads are grouped into what are called workgroups, and threads inside workgroups have different properties than threads across workgroup. We are interested in what happens with threads across workgroups. There are different ways to synchronize threads when they are inside the same workgroup or even at a lower level inside the same subgroup. And just as a final bit of background, I want to briefly mention some progress models that prior work has proposed. This is prior work that was done by me and some of the collaborators on this paper in Concur 2018. These progress models are presented as theoretical models, so there wasn't actually any testing done in that work. But some of these progress models are pretty interesting that they've proposed. They propose 3 progress models. One is called OBE, or occupancy-bound execution. That means that once a thread starts executing, it's going to continue to be fairly executed. That is, it will never be unfairly preempted. Another progress model they have is called HSA, or heterogeneous system architecture. This is named after a GPU framework. And what this says is that the thread with the lowest ID will continue to be fairly scheduled, but threads with higher IDs may not be fairly scheduled. And finally, they present a combination of these two progress models called LOBE, or LOBE, which stands for linear occupancy-bound execution. This means that all threads that have executed at least one step will continue being fairly executed, and any thread with a lower ID than a thread that is being fairly executed will also continue being fairly executed. And this is the progress model that prior work proposed described modern GPUs. The first tool in our toolbox that I want to talk about is the executable semantics for progress models. This is encoded in the CADP model checker. How this works is, given a program, it checks if that program is guaranteed to terminate or not. And it does this by reasoning about an LTS, similar to how we looked at the mutex, except the LTS is augmented with some extra information. This information is a set of IDs at the end of each edge that says which thread is guaranteed fair execution. So this is an example with HSA, and that means that the thread with the lowest ID is guaranteed fair execution until it terminates. So you can see thread ID 0 is guaranteed fair execution up until this point, where thread 1 is until the end of the program. Now, what the model checker does is it checks for cycles where the cycle consists of fair threads executing that cycle. So here we see T0 is executing this cycle, and it is a fairly executing thread. So there's potential for non-termination here, and the model checker will report that. Our second tool is test case synthesis. So what we've done is we've encoded the semantics of a small concurrent language in the alloy analyzer, and we've done some synthesis constraints over an LTS. In particular, we've said that each LTS has to have a start state in blue, and there needs to be at least one cycle in the LTS. However, this cycle must always be possible to terminate and make it to an end state, which is given in green. Now we have some heuristics for efficient synthesis. Specifically, we have a very small local state. We don't keep track of registers, only a program counter. And we have a very small global state. Usually we have only 1 or 2 memory locations. Now, using this test case synthesis, we were able to synthesize 483 tests. You can explore these at a web page that Lucas Salvador set up right here. The tests are on the left-hand side, and the LTS with those tests are given graphically here. Now, just because we all know synthesis can be a bit diabolical, I have 2 more examples of some of the crazy tests that the synthesis was able to produce. So we find those to be pretty interesting. And now we're to the point where some of our tools can start to synergize. Specifically, we're going to feed our synthesized tests into our executable semantics and create partitions of these tests. So the first partition that we do is we're going to check to see which tests have starvation cycles and which tests have live locks. We can see about 65% of our tests in this purple bar have starvation cycles, while a fewer, but still a decent amount, have live locks, which are these green tests. So then once you do that, you can take those tests and you can further divide them into conformance test suites for our different progress models. So you can see HSA here has 90 tests that we can use as a conformance test suite. OBE has 12 tests. LOBE has 122. And then for full fairness, we have 323 tests. These are the tests for the weak fairness variants, but we also have strong fairness variants. Now, at this point, we can take our conformance tests and we can actually compile them down to executable GPU code. Overall, this was fairly straightforward, but there were a couple of quirks that we had to deal with. For example, the language that our LTSs were in use GoTo, but some GPU languages don't use GoTo, so we had to emulate that with a switch statement and a manual PC. We also used atomic RMWs for every single memory access to force memory to go to a point of coherence. So once we did that, we were able to test many different GPUs. So we tested NVIDIA GPUs, Apple GPUs, Intel, Qualcomm, ARM, and NVIDIA. We tested through CUDA, Metal, and Vulkan. These are all different GPU languages. It was a lot of work to get this going, but we got a lot of results. And some of the surprising results we found were that ARM Mali GPUs and Apple GPUs showed violations of the LOBE progress model, which was hypothesized by prior work. So this shows that prior work thought the GPUs implemented a certain progress model, and we showed that it didn't. Additionally, folks from Apple gave us additional tests that showed violations for the OBE progress model. So that adds another dimension to that story. Interestingly, all GPUs that we tested appeared to pass the HSA progress model, so that might be a good foundation to look at. And with that, I'd like to thank you for your time. What we've developed is a toolbox for progress model specification designers. Here's some links, and we hope to chat with you soon. Thank you.